Okay, so before we start today's lecture, questions. So if there are no questions, let's just start the meeting and see what we were seeing. So we were talking about sampling of signals to get discrete time signals. So we covered all these basics about what sampling means. And then I said that we're going to cover three aspects, and for that we are going to see what is known as impulse terrain sampling. So impulse terrain sampling, what this thing is and how this thing will give us an insight into what happens once we do sampling. Three aspects. One aspect is what happens once we do sampling, what happens in time domain, and we will see graphically and we'll just write equations for that. And then we'll see what happens in frequency domain once we sample a signal, impulse terrain sampling. And we will graphically also see what happens, and we will write equations for that also. So three aspects: what happens in time domain, what happens in frequency domain, and also the third aspect is the mathematics part of it, that what all equations actually are there. Okay, so coming over to what happens in time domain, we covered this earlier also, and just to go through it quickly again. In impulse terrain sampling, we deal with what is known as a terrain of impulses, and this signal, which is an impulse terrain, is given the symbol P of t. So this is the impulse terrain, and that's the signal that you see right here. So these are impulses which are spaced at time period t. So this is delta t, this is delta t minus t, delta t minus 2t. So this is basically a terrain of impulses going all the way, and similarly on the negative side also, minus t minus 2t. So this is basically a terrain of impulses. We just multiply whatever signal is given to us with this impulse terrain and end up getting impulse sampled signal xp of t, subscript p. So this xpt that we get is your impulse sampled signal. So practically, to get this impulse sampled signal, we just multiply our x of t with impulse terrain. And what is that impulse terrain? If you just mathematically write it, it is just a whole sum of shifted impulses, unit impulses, which are just shifted. So these are just unit impulses which are shifted in time, and this is basically sum of those unit impulses. And if we just replace this P of t with this summation, we end up getting this equation right here, which is x of t multiplied by P of t. X of t can come inside the summation, and this x of t, once it multiplies with this impulse terrain, then we end up getting values which are scaled impulses. Okay, so this product end up giving you this right here. So the values will exist only at multiple of t, and this is the resulting scaled impulses. Now talking about P of t and covering the second aspect, which was seeing it in frequency domain. The first thing that we do is we see that P of t is a periodic function. These are just impulses which are repeating after time period t. So because these are periodic, we can write a Fourier series for that, because Fourier series is for periodic signal or function. So for periodic series, we need to find the coefficients of periodic series. This is the formula that we use to find the coefficients of periodic series, and just to write that formula here, it is 1 over t times integral over a single time period of your function, which in our case is P of t, e raised to power of minus j k omega naught t dt. And then taking one time period from minus t by 2 to t by 2, this will end up giving us a single impulse delta t in this time period. And this integration, this whole thing we have seen, ends up giving us just 1, because delta multiplied by anything will end up giving you a single value. This delta t value exists in this entire duration while it exists only at t equal to 0. So at t equal to 0, we end up getting the value 1 here and value 1 here. So the whole thing is just 1. So ak is just 1 over t for all k. Now from this ak, we can just write Fourier transform. So how we can come from this point to this point, that I covered, and that is a very interesting aspect. So if I just go over what we were doing earlier and show you that how we can come from AK to Fourier transform, that thing will be interesting. This is what we were seeing last time. So let me just go over the whole thing again. So this is that P of t. So P of t, impulse terrain, and these are just delta t's which are shifted at time period t. So this can be expressed as Fourier series, which is sum of complex exponentials, and the coefficient part can be computed using this formula right here, and we have seen that this ak ends up giving us 1 over t. So if we just plot your ak against k, this is the graphic representation of Fourier series. So this is having value 1 over t throughout. Now to come from ak to this pj omega, 0 corresponds to 0 on the k-axis, and comparing k-axis with omega axis, this plus and minus 1, these are basically the first harmonic, the complex exponential of first harmonic. So 1 is equivalent to this omega s here, minus 1 is minus omega s, and similarly 2 is 2 omega s minus 2 omega s. The other thing is that if this value was 1, this value would be 2 pi. The relationship between these two is that your a and the value of complex exponential right here on omega axis is having this scaling factor of 2 pi. If this was 1, this would be 2 pi. If this is 1 over t, this will be 2 pi over t. So all these impulses end up giving us impulses on the omega domain, which will be located at multiples of omega s and having value 2 pi over t. Now this 2 pi over t is also omega s. So we see that if we just write down pj omega, it will be this omega s times delta omega, single impulse, and then impulse shifted by omega s, omega minus omega s. So this is shifted impulse, omega minus 2 omega s, the other shift, and the values throughout are omega s. So if we just write it as summation, it ends up giving us this omega s and sum of this shifted impulses delta omega minus a multiple of omega s. So this is your Fourier transform right here. So the same thing we could have done using a simple this integral formula also. Using integral formula, if you had just replaced the value right here, that also will end up giving you more or less similar thing as you see earlier. Okay, so the other aspect was xpt is basically multiplication right here. Now if we take Fourier transform of this product, it would be xpg omega on the left hand side, Fourier transform of xpg omega. On the right hand side, x of t will become xj omega and pt will become pg omega, and this multiplication ends up becoming what we call as the circular convolution, and this circular convolution is nothing but scaled convolution, 1 over 2 pi times convolution. So one formula we have already seen for convolution, that is that if you have convolution in time domain, if you take Fourier transform throughout, then this convolution will get changed to multiplication. This is what we already know. So if you have multiplication, that ends up becoming convolution, but a scaling factor of 1 over 2 pi ends up coming up. So this is just the linkage between the Fourier transform of multiplication and Fourier transform of convolution. The other thing, this was one aspect. The other thing, the background knowledge that we need to have is anything convolved with an impulse will give you the same thing back. Whether you do that in time domain or you do it in omega domain, anything convolved with an impulse will give you the same thing back. And if you convolve any function with a shifted impulse, t minus t naught, shifted by t naught, then you will end up getting the shifted function x of t minus t naught. So this again is valid for this omega domain also. If xj omega is convolved with a shifted impulse, the end result would be the whole xj omega will get shifted in omega domain by omega naught. So this thing is very useful, and we are going to use this right here because we see that pj omega has to be convolved with xj omega, and we have a scaling factor of 1 over 2 pi. So once we do this convolution, what should we end up getting? And that is what we will see right here. So pj omega, if you see, is basically set of impulses which are shifted by a multiple of omega s. This is what pj omega is, k equal to minus infinity to infinity. Now, if you want to convolve this with anything, we can just expand it. First of all, this constant, we can just take it out. So this, if you want to do this convolution of this with this, then omega factor we can just take out and just say that this is omega s over 2 pi, and inside you will have this convolution of xj omega convolved with this whole summation right here, which is k equal to minus infinity to infinity, and these are impulses, omega minus k times omega s. This is what you will end up getting. Now you can expand this whole thing that you have right here. We could have written it in expanded shape also. So these are just a sum of impulses. Now xj omega convolved with an impulse will give you the same thing back. Convolved with a shifted impulse will give you a shifted version of this. So, and this omega s we know is just 2 pi over t. So if we just write omega s as 2 pi over t and have this 1 over 2 pi with it, multiplication, and inside you will see that this will just end up giving you k equal to minus infinity to infinity. It will be just this xj omega copies shifted by k times omega s. It will just give you copies, and this 2 pi should cancel out. So end result is that your x pj omega is just 1 over t times sum of shifted xj omegas. So this is what we will end up getting. So this is going to be the Fourier transform of x pj omega, and that is what we see right here also. So this is what we see right here, that your x pj omega is basically your what was it, xj omega convolved with pj omega and a scaling factor of 1 over 2 pi outside. So it is just this. And how did we get this? This actually came from right here, because xpt was simply multiplication of x of t with p of t. And if you take the Fourier transform of this thing, take your Fourier transform on both sides, it would be xpj omega would be Fourier transform of this, Fourier transform of this, and circular convolution, which is 1 over 2 pi times convolution. So if you just take 1 over 2 pi outside and do convolution, simple formula, integral type also, you will end up getting the thing that you see right here. So here they are just using that convolution formula, x j theta p j omega minus theta d theta. You can use tau also if you want, but it is using the theta sign here. So this is that, and if we just plug in values for pj omega, then pj omega is basically just shifted delta functions, and with the omega as scaling factor which is taken out, and omega s ends up giving you 1 over t. And inside, if you just take summation out and integration inside, you end up getting this xj theta multiplied by these shifted impulses d theta. So these shifted impulses multiplied by anything will give you the same thing shifted by the same amount, which is k omega s. So end result is exactly what we saw in the separate slides, that xpj omega is just 1 over t times shifted versions of xj omega and located at multiples of omega s. So what this means and what this actually graphically means. So if we have, let's say, xj omega, which is given right here, this is basically the Fourier transform of your x of t. So whatever function is given to you, if the Fourier transform of that is, let's say, xj omega, which is shown right here, and mind you that this is just showing you that this has got a particular max value. So if we have this x of t, which is band limited or has some maximum frequency content, let's call this omega m, and in between it can have any shape and form. Here they have shown a triangle, but it can be any shape and form. But it's just showing you that from DC it goes all the way to a max frequency somewhere here. So this is the Fourier transform of your given signal. And if you want to impulse sample it, then the end result that you will get would be this xpt, and xpt, the Fourier transform of that would be the same xj omega, scaled by a factor of 1 over t and having copies at multiples of omega s. So it will be having copies at omega s, 2 omega s, minus omega s, minus 2 omega s, like that. And if this was, let's say, here it is showing you 1, but if you had any amplitude, that amplitude will get scaled by a factor of t. In this particular example shown, they have selected a signal whose xj omega value was 1. The time period t is also selected as basically 1, so that's why you see 1 here and 1 there. Okay. So this thing is very interesting and very important for us to understand that what happens once we do scaling, once we do impulse sampling. So once we do impulse sampling, we end up getting, let me just draw a line right here and say that this is your time domain. So whatever signal is given to us, let's say x of t, it can be any shape and form, whatever shape and form it was. And this x of t will get multiplied by p of t, which is your basically set of impulses, which will be your set of impulses going on and on and on. Having value 1, location at t to t and all that. So in time domain for impulse sampling, we just multiply these two signals together and get your impulse sampled signal. So xpt is nothing but multiplication of the two signals right there, and we end up getting as a result your scaled shifted impulses. So this is your xpt. So in time domain, this is what impulse sampling is. So in time domain, we just multiply your signal with, and impulse terrain is basically your shifted impulses, infinite set of shifted impulses, which are just multiplied by this, and we end up getting as a result scaled shifted impulses. So this is what we get once we do impulse sampling. This is what happens in time domain. Now in frequency domain, if you want to see that what's going on, what happens to the frequency content. In frequency domain, the Fourier transform of each are taken and shown right there. So whatever signal is given, if that signal is having a particular frequency content, so we can just plot that against omega. So this is time domain, where domain is having variable t. This is frequency domain or omega domain. So let's say that your maximum frequency content were there for your given signal, and your given signal had a particular maximum frequency content. Let's call it omega m. So it will have a particular, let's say, shape inside this. In the example, they are giving it as a triangle, but it can be any shape or any distribution of frequency in this particular signal of yours. So this is your xj omega, having a particular frequency content from DC value to some max frequency omega n. Now, for P of t, we have seen that once we actually take the Fourier transform of P of t, what we end up getting is again a set of impulses, and the set of impulses are again having a particular, let's say, 0 omega s minus omega s, and this goes on and on. So, and the value here is again omega s. So this is what we saw was Pj omega. So Pt was also set of impulses with value 1. This is also set of impulses with value omega s. So these are, mind you, impulses in time domain. These are, mind you, impulses in frequency domain, delta omega, but scaled by a factor of omega s. Okay, so multiplication sign right here, it ends up becoming what we call as the circular convolution. And it is convolution, but with the scaling factor of 1 over 2 pi. So the end result that we get once we, let's say, do circular convolution or convolution with scaling is, first of all, we need to see this thing. These are set of impulses. Now we can break it up into individual impulses and do, let's say, convolution with each, and then all the results can be added together. So if you think in that way, if we convolve with this impulse, which is a single impulse, you should get the same thing back scaled by the factor omega s right here. So if, let's say, this was having an amplitude A, you will see that the first thing that you will get would be something like the same thing to the same value of omega m minus omega m. So the same thing back, but this multiplication factor and scaling by 1 over 2 pi. This omega s that we see is basically 2 pi over t. So once we scale by 2 pi, we end up getting A over T right here with this impulse. Similarly, if you see this impulse centered at omega s, it's a shifted impulse. This convolved with this will give you the same thing located at this position. So it will end up giving you the same thing located at this position, and obviously having the same value right here, omega s. And similarly, we will get copies right here also. So each impulse will end up giving us copies like that, and it will go on and on and on. So this is the end result that we get, which is your xp j omega. So this is what we need to understand. So Fourier transform of this is actually this. So we see here, this is what happens in time domain once we do impulse sampling. This is what happens in frequency domain. The same signal, if we see in frequency domain or in omega domain, you will notice that these are the frequency content of your original signal. These are the frequency content of P of t. These are the frequency content of xp of t. And if you see, there are basically two things happening once we sampled or impulse sampled our signal. We ended up getting two, you can say, aspects right here. One, we ended up getting copies of these frequency contents at multiples of omega s. So we had a copy here, and again we had a copy here at 2 omega s, like that. So we had copies at multiples of omega s, the first aspect. So the first aspect is copies at multiples of omega s. The second aspect is basically the scaling part. Scaling by a factor of 1 over t. So these two aspects happen once we do impulse sampling. Your signal, first of all, gets copies at multiples of omega s, and you end up getting scaling by a factor of t. So if this had a value or magnitude a right at this point, the magnitude here would be a over t. And at any point, whatever magnitude is there, that magnitude will get scaled by a factor of t. Rest, the frequency max remains the same. So this is what happens in impulse terrain sampling. Now, the other aspects, let me cover from this slide first, and then we come back to this again. Okay, so the same thing is shown right here also. So if you have a signal x of t given with frequency content given by xj omega, if you do impulse terrain sampling, then the impulse terrain frequency content also would be a set of impulses located at multiple of omega s and having the scaling of omega s. And the impulse sample signal that results its Fourier transform, once you see the frequency content of that, you see that we end up getting copies of these frequency content at multiples of omega s, and all these copies are basically scaled by a factor of 1 over t. So this is what happens. So we end up getting superposition of shifting replicas or copies of xj omega, and all of them are scaled by a factor of 1 over t. So we end up getting copies or replicas, and we get scaling factor of 1 over t. This is what happens. Now, if you want to get back your x of t from xpt, from here you want to go here, or in other words, if you want from here to go back here. So how to recover your original signal back from impulse sampled signal? That interesting thing is there, that how do we actually get back our original signal from impulse sampled signal? For that, if you see this right here, so this was your frequency content original, this is your impulse sampled, Now, if you want to get back your original contents from this one, we know that we have copies here, so additional copies, higher frequency contents are there, and we have a scaling factor right here. So what we need to do is we need to pass this signal through a low pass filter having amplification factor of T. So we need to first of all pass it through low pass filter so that high frequency contents gets cut out and only this is left. The second, these values have to be amplified by a factor of T. So together we need the response of filter like this, that it should have a particular cutoff frequency. And this cutoff frequency should be such that it should cut out the higher frequency content and leave out your original signal right here. And so from all the way from minus infinity to this, all the signal contents will get multiplied by 0. Between 0 and omega c, the contents will get multiplied by a factor of T. So we end up getting our original signal back, which is xj omega. Here it is xrj omega because we are calling it as recovered signal. So this is how we can do what is known as reconstruction of your continuous sine signal from impulse sampled signal. So this is a very useful information because this actually allows us to go from, let's say, normal signal to impulse sampled signal and then come back from impulse sampled signal to original signal. So the discussion here is actually telling you that if your signal given to us had got a particular max frequency, let's say omega m, then what we need to do is we need to first of all, once we are going from this normal signal to impulse sampled signal, then this sampling frequency that we are selecting, omega s, is very important because the copies that we are going to get are going to lie at multiples of omega s. So once we do impulse sampling, if we select appropriate time period such that your sampling frequencies basically is 2 pi over t, such that your sampling frequency is quite high, or in other words, time period has to be low enough so that sampling frequency is high enough, so that once we get copies, these copies do not overlap. So if you notice here, this will be your omega m, this is 0, this is omega s, this is omega m, and right here is basically, let's say, half the value. This is basically your omega s by 2. So if we have selected appropriate omega s, then you will see that the copies that you're going to get would be very clean copies and they will not sort of overlap each other. When sampling frequency selected is not less than, is more than, actually, this, please correct it. If sampling frequency selected is more than twice the band limited frequency omega m, then there will be no overlap. If your omega s is more than twice, if you see half omega s is basically greater than omega m. So what it means to say here is that sampling frequency should be greater than twice omega m. And from this point we can see that your omega s by 2 has to be greater than omega m. Both of them mean one and the same thing. If your half sampling frequency is greater than omega m, then the copies are not going to overlap. We are going to get a very, very clean copies, and once impulse sampled signal is obtained, in frequency domain you will see very nice clean copies of frequency contents which do not overlap. So if sampling frequency selected is greater than twice the maximum frequency, then we can get our original signal x of t back from impulse sampled signal x of t, xp of t, by passing it through a low pass filter whose gain or amplification is t, and cutoff frequency is between omega m and omega s minus m. So we just select cutoff frequency in between your omega m, and this point here is your omega s minus omega m. So cutoff frequency will lie right in between here. So the best point to choose is basically your omega s by 2. Typically we choose cutoff frequency exactly as omega s by 2. So once we do that, then we can get our original signal back. So this is what is known as the sampling theorem also. So this sampling theorem we have already covered it, but let's just specify that what is sampling theorem. It says that if you have a signal x of t which has got a particular max frequency, that means it is basically band limited or frequency limited. It has got a particular max frequency. All the frequencies are below this. Then we can get your x of t sampled such that the sampling frequency is greater than 2 times omega m. If we select this sampling frequency, then we will be able to recover your signal back from sampled version. Now this omega s, which is greater than 2 times omega m, this rule was given to us by a scientist named Nyquist. The limiting case of this would be that your omega s is equal to 2 times omega m. So this 2 times omega m is basically the Nyquist rate, or the minimum possible sampling frequency if you want to reproduce your original signal back. Because here if you see, if your omega s was exactly equal to 2 times omega m, the second copy will start right here. It will be just touching right here. So second copy will be something like this. So omega s is equal to 2 times omega m. And if it is greater than that, then you will have gaps right here. Half omega s will be greater than omega m. So the minimum possible sampling frequency is basically twice omega m. And if you select omega s less than that, you will end up getting what is known as overlaps, and your signal will not be able to recover back your signal completely. So this 2 times omega m is known as the Nyquist rate, as this actually tells us the omega m, largest omega m frequency that can be reproduced with a particular sampling time. Now this actually gives us that strength of selecting time period t, because time period t is basically 2 pi over omega s, or in other words, sampling frequency, we can call it fs, is basically 1 over t, and omega s is basically 2 pi times fs. So all these linkages are there. This actually answers that original question. If you remember, once we were talking here, if we have, let's say, 3 signals, green, red and blue, RGB, red, green, blue signals, and we had to select a particular appropriate time period for sampling, time period t. The question was, what is the appropriate time period t that we should select, so that once we have sampled signal, we should be able to recreate your original signal back from sampled version. So how close should these samples be? How close should these samples be? The time period t, what should be the time period? This is answered now, because this is answered in terms of the sampling frequency. Now the sampling frequency that we select should be greater than, or in limiting case equal to, 2 times omega m. And t is basically 2 pi over omega s. So this is how we select our sampling time period. Now this is something which we engineers are supposed to know, that whenever we do conversion from continuous time to discrete time, at what rate should we select the samples? What should be the sampling frequency, or how many samples per second should we take? So if you're talking about samples per second, that is the frequency in hertz, that is 1/t. If you're talking about time period, that how should these samples be spaced, or distance in between samples in terms of seconds, that is your sampling time period. And angular frequency, angular sampling frequency is omega s. So these all aspects was actually given to us by the scientist by the name of Nyquist. He actually said that in order to properly sample a signal, so that after sampling you should be able to recreate the original signal back, in that particular case, the sampling frequency should be selected such that it is greater than or equal to 2 times omega m. If it is equal to 2 times omega m, that is known as the Nyquist rate. That is the minimum possible sampling frequency, or the optimal rate, as we say. Okay, so this actually completes our sampling or impulse terrain sampling. Questions? Any questions? No questions. Everything is clear. Okay. Now the very last slide, I will cover that also. So if you see here in impulse terrain sampling, this is more of a theoretical type of sampling, because we need to come up with impulse terrain. First of all, getting impulse itself is theoretical, and getting an infinite set of impulses, the signal p of t, again purely theoretical. So first of all, if you need to do impulse terrain sampling, then we need to somehow come up with your impulse terrains and then multiply that impulse terrain with x of t to get your impulse sample signal. Actually, your x of n, your discrete signal, x of n, sorry, your discrete signal is basically the values that you have right here. So our interest is basically to come up with these values so that we can somehow store that and keep a record of that. Now, how do we somehow get these values? Because your impulse terrain was more of a theoretical thing. So this actually, in real world, the ICs that you use, which convert from analog to digital, they do what is known as zero order hold sampling. In zero order hold sampling, instead of going for this impulse sampled signal and somehow trying to retain the value or record this value, what we do is, because we know that it is difficult to generate or transmit narrow large amplitude pulses or impulse terrain. Not difficult, is rather impossible. We cannot have impulse. Impulse is a theoretical signal. What actually happens is they actually do zero hold sampling. In zero hold sampling, we can use rather multiple different types of sampling techniques, but in zero hold types sampling, what happens is we actually record the value of the signal at particular time period. Here if you see, the values were supposed to be taken at this time period. Here also we are doing the same thing, but instead of just taking instant value, we take this value and this retain this value, and then at time period t we again record the value and then retain the value, and then again at next time period record the value and then retain the value. So this way we end up getting this type of a signal right here. So this is your zero hold sampling signal. So impulse terrain sampled signal or impulse sampled signal, zero hold sampled signal. Now seemingly this one is sort of distorting this shape here, but our interest is not of the shape. Our interest in x of n is basically just the values here. So what is the value here, what is the value here, what is the value here, that is important for us. So this is equal to the value here, value here, value here. So in zero hold sampling, instead of just having an impulse or scaled impulses, we just retain that value. And this is more practical, and in your ICs, this is what is used for keeping a record of your value for discrete signal. So this is just introduction to this. We are not going to cover that in detail. All the theories are covered in just impulse terrain sampling only. Okay, so this actually completes the slide set number 10. And in this, actually, we covered sampling of continuous time signal. And we saw what happens once we do impulse terrain sampling, what happens in time domain, and what is going on in frequency domain. And we wrote down equations for all that, time domain and frequency domain signals. Next, we also saw what is the appropriate sampling time period and what is the minimum possible sampling rate, which is known as the Nyquist rate. And that actually sampling formula, sampling theorem, we actually came up with this, and this was given to us by Nyquist. And again, somehow this sign is missing. So omega s has to be, sampling frequency has to be greater than or equal to twice the maximum frequency. Okay, so we also actually covered or just introduced zero hold sampling. In real world, mostly the conversion is done using zero hold sampling. Okay, so this actually covers our complete set of slide. So let's have about 10 minutes break, and then we come back again and have a quiz then. So just take about 10 minutes break, and once we come back, we will do quiz. So we have a periodic signal x of t. Okay, so we are given a periodic signal x of t, and what we need to do is we need to find out, first of all, the frequency contents of the signal. And the V part is magnitude of let's take what? Let's take 10 Hertz. Okay, so as per my clock, it is 3. So how much time you need? It is not more than about 5-6 minutes if you know how. If you don't know, you can take the whole day. It won't matter.